Bill, we didn't do our training. We did not do our training, but I don't think it needs to be. So you just arbitrarily change these things, okay?
Yeah.
Okay. All right. Yeah.
Program, I wrestle them all.
Okay, that's good. Yeah, that's good. Thanks, Earl.
Let's begin. It's my privilege to welcome you to the University of Tennessee Nuclear Engineering Department Colloquium Program. Today's speaker is Dr. Bill Stacey, who is the Callaway Regents Professor of Nuclear Engineering at Georgia Tech. Bill received his BS and MS in physics at Georgia Tech in the early 60s, and then received his PhD in nuclear engineering from MIT in 1966. His degrees at Georgia Tech were in physics. He spent 8 years working at the Knowles Atomic Power Laboratory, which is in Schenectady, New York, Naval Nuclear Power Propulsion. And then he spent 8 years at the Argonne National Laboratory. And then he came back to Georgia Tech in 1977 and joined the faculty in the Department of Nuclear Engineering as the Callaway Regents Professor of Nuclear Engineering. And he's been there ever since, working primarily in the fusion field. He's also the author of a couple of books, a new textbook on reactor physics, which we used for the first time this year in our graduate course. Bill is a longtime friend. I first met him in 1969 when I was a very young graduate student, and he was a distinguished professional in the field, and we've been friends ever since. And so it's indeed a pleasure for me to introduce to you Dr. Bill Stacey. Bill, welcome.
Thank you, Lee, and thanks for the opportunity to come to the University of Tennessee. I think that was the time Lee's talking about was the last time I gave a seminar here. It must not have gone over too well. That's the first time I've been invited back since then. And I've already caused trouble with the projection equipment. This is the one view graph I'm not going to use. So you'll see it. So, autofocus.
Yeah. It'll focus. There you go. There.
All right. So this is what I'm going to talk about, is transmutation of spent nuclear fuel. I'm going to talk about it a little bit in general, and then a little bit specifically on some of the work that we've done at Georgia Tech in the last couple of years on this subject. Let me first give a little motivation for why this is important. And I should say that I've included more information on these view graphs than I'm going to be able to talk about, in hopes that anyone who wants to know about the details will look at them in whatever form they're stored in after I've messed up the system later. Okay, the motivation is that we've got too much nuclear waste, and we're producing it at a rate such that if we just keep on producing it at the current nuclear power output rate, we'll have to build a new Yucca Mountain every 30 years. And so we should see if we can do something about that. The thing that really determines the capacity of a repository is the heat, the decay heat that comes out, and to a much lesser extent, the radioactivity associated with it. And so what the idea of the transmutation is that the decay heat and the radiation for the first few hundred years is mainly fission products, but after that, it's the actinides, plutonium, and the higher elements. And so, if you can get rid of them, basically fission them and turn them into fission products, then you can transform a 100,000-year problem into a 1,000-year problem. So that's the idea of transmutation. And then when you start looking at it a little bit more, you can go through, and so what you have to do is keep recycling this stuff. Keep sending the actinides into a neutron source until you fission all of them. And, of course, you're going to have materials damage that limits you before that happens. So you're going to have to reprocess. But if you do this continuously or repeatedly, what you can do is end up sort of reducing by a couple of orders of magnitude the amount of stuff, either in terms of heat or in terms of mass, that you have to put into a repository. And so even if you can reduce it by an order of magnitude, your every 30 years goes to every 300 years. You have to build a new repository. So it's worth taking a look at. Just on the way in, a little bit of a diversion here on what we actually do with the energy content of uranium as it comes out of the ground. About 83% of it we just set aside after we enrich the uranium. This is what's left in the enrichment plant. We fission about 0.6% of it. We discharge about 17% of it. And then in the actinides, this discharge, we've got 0.2%. Let's see, is there a...
Yeah, I need one.
So this is how much energy we're making use of right now. And we've got this in the actinide. So if we do this transmutation in the same time that we're getting rid of the problem of waste repository, we're getting another 30% of energy. Just something to point with. So,
Laser point.
yeah,
I got that.
yeah. Okay, here's one of these. There's lots more information than you really need to know, but just focus on the first two columns. This is what's in spent fuel, at least is the uranium and actinide contents. Most of the uranium has been separated out, but you've got trace amounts left. But about 75 or 80% of it is the various plutonium isotopes, and then you have the various higher isotopes. All of these things have a fission cross-section. And so if you want to get rid of them, you have to fission them. If you just capture a neutron in them, then they go to another one. So you've literally just wasted a neutron, because you're going to have to get rid of that too.
Old technology.
Okay, all right. I think we can right started on this. Okay, so this is just in the way of background. This is what's in it. Now here is a little measure of what the problem is that we're looking at here. So this is radioactivity measured in a couple of ways. So from time after discharge, this is the radioactivity level, and up here it's almost all fission products up for the first several hundred years. That's where all the radioactivity comes from. Then the fission products die away, and after that it's the plutonium and the higher actinides. And if you really want to know exactly what it is at what time, you can play that out too. But the message here is that it's fission products for the first few hundred years, and after that, it's other stuff that has a fission cross-section that can be converted to fission products. So, how to get rid of it? You get rid of it by fissioning it. Does everything have a fission cross-section? Yes and no. This is the fission probability of all of these various things. Can you actually see these things? Okay, so this is U-235 on in order. The crosshatched is the probability of fission if a neutron gets captured in a fast spectrum. The white is the same probability in a thermal spectrum. And so you can see that in a thermal reactor, there are a lot of these things that are just not going to fission. But they all have a significant fission probability in a fast spectrum. And so, fast spectrum. All right, what have people been doing about this? For the last roughly a decade or more, there's been a lot of interest in this worldwide, particularly in Europe, but also here and in Japan. So there have been a lot of studies of fissioning these isotopes. And there are several ways you could do it. You could just simply reprocess it, put it into mixed oxide fuel, and put it back in a light water reactor. Try that. Keep on doing that. You could put it in this, now that's a water reactor, so it's going to have a thermal spectrum, so it's going to work, but not so well. You could build a fast reactor and do it in the fast reactor. You could build a subcritical fast reactor and drive it with an accelerator. and you still got a fast reactor. It's just one that's subcritical. And so there have been an awful lot of studies on those sort of things. And I'll show you right at the end some references, lots of reports and conference reports and websites and whatnot where all of this was documented. In the U.S., there's been a lot of work that has concentrated on using basically the argon integral fast reactor concept, which is a metal-fueled, liquid metal-cooled reactor, with the argon pyrometallurgical processing techniques to accomplish this, both in a critical reactor and in a subcritical reactor driven by an accelerator source, and I'll refer to that as ATWR, and the critical reactor is the integral fast reactor. So this has been where most of the work in the U.S. is concentrated in the past. This is changing now, but up to now, this is where the action has been. As Lee said, I'm interested in fusion. It occurred to me that fusion makes neutrons too, and might actually be a little bit better neutron source than an accelerator. Probably get some argument from some people on that, but at any rate, a few years ago I got interested in it with the idea of, well, hey, let's see what fusion could do for this too. So we've had an effort at Georgia Tech for the last couple of years, and there are a couple of other people around the country that are looking at this sort of thing, and I'll tell you a little bit about this in the process of going through and telling you a little bit about this. All right, so what are those reactors that we're talking about? We're talking about basically the reactors that the U.S. has been looking at. So the integral fast reactor basically is a cylinder about 1.5 meters in radius and about 0.5 meter tall, 840 megawatts, sodium-cooled ferritic steel clad material. And the fuel in there is uranium plus whatever actinides that you're putting in, plus what I showed you in that second view graph. And in fact, it's 72% uranium and 28% TRU is a buzzword for transuranics, the stuff we want to fission. Okay, so this has got 72% U-238 in it. So that means a reactor like this has as its purpose to destroy the actinides. It has the U-238 in it because it needs the Doppler effect for safety. But having the U-238 in it, there are going to be a lot of neutrons captured in U-238, and what are they going to do? They're going to produce actinides. Okay? So they're going to cut down on the net destruction. And so one of the ideas of operating subcritical is to leave the U-238 out. Because if you've got a bigger margin to a runaway, then you can afford not to have that fast Doppler, or at least that's the postulate. So the accelerator thing is the same thing, except the accelerator target is something like Yay that sits in the middle, and then that's surrounded by an annular reactor. And you can see the dimensions here, and it was designed to be at the same power, and it uses the same fuel, except it just has just the transuranics that you want to destroy. No uranium, but basically replace the uranium by zirconium in there. So we're not, in this, we're not going to make anything. And then we looked at this and said, okay, well, we'll do the same thing. We'll have the same type of technology. And so we're going to use exactly the same fuel as here. Well, I should say this is lead bismuth cooled. This one was sodium cooled. And I see here my secretary invented a new coolant. But this is really lead lithium cooled down here, because in a fusion device you need to make tritium, so you need the lithium. And so that's what we added to. So I'm going to show you during the course of the talk some comparison of the performance of these different things, at least to sort of isolate what is important about the differences. But first, I have a colored picture of our fusion design, and this actually, I see all the design prizes along the wall here. This actually came out of our senior design class a couple of years ago, where we sat down and designed a fusion device that would do this job. So this is sort of a standard tokamak. These are magnetic field coils around here, and then the plasma goes around in a donut-shaped configuration like that. And then the reactor is sitting right out here. Okay, so it's right outside the plasma, and it runs all the way around. Funny reactor, but with this geometry, that's where it goes. And so this is the subcritical reactor we're going to put out there. This particular design is with copper coils, and you can get those down to about 3 meters from here to here. So that's the dimension on this thing. All right, these forget the numbers unless you're particularly interested in fusion. Those are for people that will look at it later. But the philosophy of coming up with this design was to avoid pie in the sky, which is what fusion is usually accused of. So we took, for the design of that device, we took the existing physics database, the same thing that ITER's being designed on. So physics that's already been achieved. And we took the existing physics technology, which Dr. Shannon has actually been involved in developing, along with other things. And so this is existing technology with one exception. The lead-lithium technology is not there yet, but the lead-lithium technology, in fact, is heavily under development, especially in Europe, for fusion uses. And then the next question is, okay, so you've already got that technology. If I were talking to a fusion artist audience, they would say, hey, but we're on a track to develop electricity, and we don't want to be diverted by something like this. Well, this is on the track, because you need exactly the same technology, and everything you learn here is going to help you on the path to electricity. And in the process, we're very soon going to hear an announcement that this first-generation fusion plant is going to go ahead, and the U.S. is going to join it. High probability for the first, a little bit lower probability for the second. But at any rate, this sounds like it's going to happen. So this device might break ground for construction by next year, would serve as an excellent prototype for this. It does all the things that you need to do in a prototype to handle, to be ready to move into a transmutation reactor of this sort. Again, a little bit more detail on this than you probably need, but we looked at two designs, one with copper magnets, which I showed you, and another one with superconducting magnets. And in the reactor, we're looking at this zirconium and transuranics alloy metal fuel. We're using ferritic steel for clad and structure, and we're using lithium lead. For the coolant, we looked at another option where we would use lead bismuth because the accelerator design was like that. But our primary option is this. And I don't think the structure of the material of the magnets are particularly relevant. Okay, coming back to the reactor, what does it look like in a little bit more detail? So again, here's the tokamak, and this belt that's running around the outside is the reactor, and you can see it in a little bit better configuration here, and I'll give you the numbers on this on the next view graph. But what you see is this belt running around here, and this is the belt. And the belt is made up of fuel assemblies. And these are the same fuel assemblies, except for the height, as the ones that Argonne has designed for the integral fast reactor and for the accelerator reactor. So we're talking about using existing nuclear technology at this point. We're not inventing some miracle material or miracle design or anything like that. We're taking the nuclear technology that's being used for the other U.S. designs. And so this thing just simply wraps around. Okay, just a little bit of detail. Well, you can remember what this is. This is the same picture that was on the other one. So each of these assemblies here has got 210 fuel pins on it and 7 structural pins. The thing is 2¼ meters in height, and from the cross flats of one of these assemblies is 16 centimeters. There are 470 of these assemblies as you wrap around the outside. And then we just took the Argonne design, so there are lots of detailed numbers. This has been looked at in detail. the heat removal and all of that, and it actually works. In fact, people that do it better than we do, but we also look at that. Okay, so one of the things that I alluded to earlier that was that maybe operating subcritical instead of critical has some advantages. And so one of the things that we did was to take a preliminary look and see if there is any advantage of operating subcritical. So this is just plain old linear stability analysis for the stability of the reactor. What we're plotting along here is the fuel temperature coefficient, and along here is the coolant temperature coefficient. And if we had a critical reactor, you can see that in order to be stable, one or the other has to be negative, as you might expect. But if you can operate somewhat subcritical, above this is unstable, below this is stable. If you can operate somewhat subcritical, then you can relax the constraints a little bit. You can even operate out here with positive temperature coefficients of both sorts, and the subcriticality pulls it down. And we're actually talking about operating max in here at 0.9, max K in here. So this doesn't point out any advantage, but it points out that there might be an advantage there, because you're not so close to critical that you've got to be so careful about what your temperature coefficients are. And remember, I said that the reason that the critical reactor has uranium in it is because it needs a prompt Doppler. And maybe the subcritical doesn't. Okay, we also took a look at what would happen in a couple of accident cases on the fusion design. So basically, if we turn the source off, an eigenvalue calculation of that ring reactor gives us, we did it for two different designs with different coolants. But let's just look at this one. This gives us, with source off, it's a K of 0.95. That's a maximum criticality condition. We've got some control rods that we stick in, and that would bring it down to like this. And now let's look at a couple of accidents. One of them is, suppose the plasma chamber just gets flooded with the coolant. Well, what this is going to do is act as a reflector to reflect neutrons back into the reactor, because the plasma chambers, the reactor surrounds the plasma chamber. So that brings it up to 0.93. For this design, it brought it up to a little bit supercritical. We didn't work too hard on this design. I'm sure that could be fixed. The other possibility of something massive happening is suppose you lose the coolant in the reactor. So you just void the core, you get in the hardest spectrum. The fission to capture increases, and so you've got a more reactive condition. And so that would take it up by itself to 0.89 or 0.90. Now suppose both of these things happen at the same time, and that comes up to this level. This is where the rod's at. So it looks like that there's a fair range there in which you can guarantee that you're not going to go supercritical. So, you know, it certainly takes much more work than this to say that, okay, it's going to be safer or anything else. But at least there's a space of hope, because you've got a range here where things just look better. Okay, now how does all of this work? Let's get into the transmutation aspect of it itself. This says the fusion transmutational waste reactor, but this is the fuel cycle used for all of the integral fast reactor, the ATWR, and this. And so spent fuel coming out here, separate out the uranium, separate out the fission products that come out, send this through a pyrometallurgical process, get the other fission products out. So what we have here going through here is the plutonium and the actinides left from the spent fuel, what I showed you there. Make a fuel element out of that. In this example, we're making a metal fuel element. Put it in this transmutation reactor. That's the FTR here. It could be the accelerator or the critical one. Burn it as long as you can, and I'll come back and talk a little bit about that in a minute. But burn it, and then bring it out. Processed out, again, through the pyrometallurgical process, get the fission products out, send them to high-level waste, and the actinides and plutonium to the left, bring it back here, mix it with the fresh, quote-unquote, spent nuclear fuel, and send it back through again, and just repeat this process. Okay, so this is the idea. We looked at this fairly carefully, just to digress a little bit. The way we decided to operate the reactor was to stay at a constant power level and to compensate for the reactivity droop with burnout by raising the source. You remember the source or the neutron population is in a reactor is S over 1 minus K, and so as K goes down, you can make S go up, and you can increase the fusion power a little bit, hence the fusion neutron source, and stay at a constant power. We use the argon fuel cycle codes, and these are fairly sophisticated things that have been developed over a long period of time that come to an equilibrium, that do a lot of iteration and come to an equilibrium fuel cycle would be. And they've got transport codes in them where you calculate all this stuff in detail. So this calculation was done seriously. And we also calculated the composition that we would start with. That one of those columns I showed you at first was one of our calculations, and so we go back here and we calculate with the scale from the LWR. So this part of it, this actually was a PhD thesis that Hoffman did. We did this one pretty thorough. A little bit of perspective on the performance of the fusion version of the transmutation reactor. Let me just concentrate on one. We've got two of them, the copper and the superconducting. But let's just look at this one. This was designed to break even on electrical power. Now, copper magnets are horrible because they're resistive, and tokamaks need lots of field, means lots of currents through resistance, and so you've got a lot of resistance losses, and you've got a lot of power that's required to get that heat out that you put in. So it's a killer. This thing is designed at 3,000 megawatts thermal. We think that would come to about 1,200. And we would basically use all of that to drive those magnets against resistance and remove the heat. Clearly not a great thing to do, but that was our design on that. And so we came out with the ratio of electrical output to electrical input of 1, which was what we were after. And if we looked at these things, never mind these numbers right now, we said how many of these will we need to support all the spent nuclear fuel that's coming out of all the LWRs. And so you can calculate this. You calculate how much comes out of an LWR, and it depends only on the power level of the LWR, and of course the enrichment. But it depends on the power level. And so you can, and the rate at which you're transmuting in the transmutation reactor also depends on the power level, because what you're doing is fissioning, and that's power for all practical purposes. So you can go through and calculate this. And this basically, one of these would support 3 LWRs at the same power level. So there's a 3-to-1 ratio. And so what that means is that in some sort of equilibrium of this sort, and this is almost independent of whether it's a fusion device or any other device. What this means is that in the equilibrium, 25% of the quote nuclear power is coming from the transmutation devices, and 75% from other devices, from the LWRs. So that's the meaning of the number. All right, we compared the 3 reactors. We were interested in fusion, so we were interested to see if we could at least do as well as the others. And there are lots of numbers here, and this is people that really want to look later. But what we've compared is what we're doing right now, the once-through cycle. One recycle as MOX fuel in an LWR, just take it out and recycle it once. And then here's the fusion, the accelerator-driven, and the critical fast reactors. Now, there are lots of numbers there, and we went through and did these fuel cycle analyses on all of these, and we fooled around with, okay, what's the best way to shuffle the fuel, and on these, and so we came up with 5 shuffles here, either 7 or 8 here, 7 here. We did the best we could come up with. The thing that's important is to look down here at what the burnup of the of the discharge after we go through a fuel cycle, how much of the original transuranic loading has been destroyed. Okay, for these, because that's not applicable here, 25% here for the MOX going through 29, 30, and 18. And then if we go through and look at the heavy metal discharge, the burnup, the actual burnup that we get, this, in other words, what goes in at the beginning, so what comes out at the end, or the other way around. Then we find that for the two subcritical reactors that we're talking about, in one fuel load, before we have to reprocess the fuel, so one fuel cycle, we can burn up about 30% of the transuranics, and then we're going to have to reprocess. In the fast reactor, it's only about 13%, and the reason for that is the fast reactor is making actinides because it's got uranium in there. And so this is going to come out as a real advantage. And of course, in these guys, which are making transuranics like crazy, you don't get much of a gain at all. So this is going to explain the curves that I'm about to show you. So this can, all of those numbers can be better seen in curves than but the explanation is there. So let's look at a few things. This is toxicity, not a terribly meaningful quantity, but one that everyone uses, and so probably most people are familiar with it. It's basically how much water it would take to dilute if we drank it. That's not terribly meaningful. But anyway, it's a number. And we're comparing this to just the toxicity of uranium ore as it comes out of the ground. So there's a benchmark. If you're above this, you're bad. If you're below this, you're good, as far as this. So the solid curve up here is the once-through cycle. So this is what we're getting right now. And you can see that we're out here almost 100,000 years before stuff decays away like that. If we do we do the single MOX cycle, it's right up here with it, so we don't get much of a gain there. It's not much gain by recycling it once in MOX. If you come to the three transmutation reactors now, the fusion and the accelerator, both being subcritical, not having uranium in them, do a better job than the integral fast reactor. And what's going on here, and what is behind these numbers, is that we're going to recycle this stuff until we fission all of it. So this is continuous forever. And where we're going to lose it is every time we have to reprocess. Every time we have to reprocess, it's an imperfect process. And so some fraction of it is going to get lost, and it's going to go to the high-level waste repository. So the more times you have to reprocess, the more you're going to lose. And the critical fast reactor has to reprocess same fuel more times because it's making new actinides as it goes. So that's the difference between this curve and this curve. So it's really the fuel. It's not that it's subcritical or critical. It's that you've got fuel with uranium in it here, and you've got fuel without uranium in it here. And the hope is that the additional safety features of operating subcritical allow you to do that. So that's really the key to that. But these look pretty good, okay? And then here we're getting down to ore in 500 years, something like that. Now here's the real result. Because as I said, the thing that sets the limit of repositories, we're going to store all this fuel, we're going to close them up, and we're not going in there. And so what's going to happen? Well, they're going to heat up. They're going to heat up because of decay heat. And so we've got to have enough natural circulation, enough volume, all of this stuff that we can remove that decay heat without something bad happening. And so this sets the capacity. It's this sort of decay heat requirement that sets the requirement on how much stuff you can put in. So here is the decay heat of the once through cycle. If we just take the spent fuel as it comes out, it's going to stay up there. If we run it through, recycle it once as MOX, it's going to not help too much. It'll decrease it a little bit. But then, if we burn up the actinides somewhere else, burn up all the plutonium and the higher actinides elsewhere by fissioning them in a transmutation reactor, then all we're dealing with here is a little bit of the actinides and the fission products. So here, this dies when the fission products die. And so you can see that there's a couple of orders of magnitude in here as we go on out. And so we're decreasing the decay heat by a couple of orders of magnitude. If this sets the capacity, then maybe we can get a couple of orders of magnitude more spent fuel in there. Now, this is just a calculation without any reality of nuts and bolts, and so let's not say a couple of orders of magnitude, let's say an order of magnitude. But it gives you some hope that you could, certainly that you could increase the capacity of the high-level waste repositories by an order of magnitude. And that means instead of every 30 years, every 300 years. Different ballgame, totally different ballgame. Okay, now let's look at what the world might look like if we were doing this. And this is a scenario, which means we sat down and said, well, how would you do this? And then we made the calculations. And you could sit down and say it, and you'd probably make a different scenario. But this is a scenario. And so what we did is said, okay, well, let's look at what's realistic. The fast reactor people think that their technology, for the reactor and for the pyrometallurgical processing, would be ready that they could start building a reactor about 2030. I think that you could say the same thing for fusion, except it's about 2040. So along about 2030, 2040, you could start building these reactors. We got the mix. You could just start building transmutation reactors. And so here's a scenario. Looks like we thought we could build one a little bit earlier. But here's a scenario, basically, where we're building these transmutation reactors. So and we're going to build them about as fast as seems reasonable. Okay, what's reasonable? That depends on who's reasoning. But this is what we looked at. And of course, these things run about 40 years, and so the reason it goes down here at the end is you're not replacing ones that are going out of commission. But we postulated some sort of scenario like this. Okay, so this is the building of them. And then what we looked at was that you've also got to say, well, what's nuclear power going to do over the next 200 years? We assume it's going to stay constant, that the amount of nuclear power produced in the United States is going to stay constant as long as this graph goes out. You could make other assumptions and you get different curves, but we just assumed it's going to stay constant. And so then we've got these reactors. So in that case, you can see this is probably about 35, about 100 reactors in the country. So that's the 3-to-1 support that I was talking about earlier when it evens out. Okay, and then the big question, certainly on a fusion device, also on an accelerator device, is how reliable are these things? On fast reactors, I think they probably can be made certainly much more reliable than a fusion reactor. Now, what I mean by reliability translates into availability. How many seconds out of the year is it actually going to be operating and doing its thing? And so you have to say something about that. You've got these, but what part of the year are they going to be operating? Because you've got a constant source of spent fuel coming out of these nuclear reactors that are going to be operating 90% of the time during the year. And so we looked at several possibilities. So here's the first one. Here's saying that you don't transmute at all. That's what we're doing now. We're just letting the stuff come out of the reactors and stacking it up. And so that's how much we're going to have. And we're looking over here. Okay. To read these curves over here. All right. Now suppose we put in some sort of transmutation reactors. And let's just say on the average, they're just going to operate 25% of the time. Something is going to go wrong and you're going to have to fix it. So it's 25%. So if it's 25%, what we can do at 25% is basically cut off the inventory of actinides, hold it level at this level. Now this is quite a bit more than we have right now, so we've got to build a couple of more Yucca Mountains in there. But okay, you see what I'm doing. So let's go to 75%, if we could ever get to 75%. Then what we would do is we would come down here and we would come to an equilibrium down there. It's much less than what we have right now. Now, does that mean we don't have to build Yucca Mountain? No, 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 no. We have to have Yucca Mountain. And so this begins to look nice. Okay? All right, here's a very, very busy summary, and let me try to give it to you in just a few words. One is that the technology is going to be there where we can start implementing these things to start operating by 2030 for fast reactors and maybe for the accelerator-driven fast reactors 10 years later. For the fusion reactors, and these are all 10 years, it doesn't change anything. So that's going to happen. I mean, that technology will be there. This, again, is more intended for a fusion audience. The fusion device that you have to build to do this can be built on the basis of existing physics, of what's already been accomplished. That physics would not lead to a good reactor that was a net electrical power generating reactor. We're still working on the physics in the fusion business to get it better. But we don't need that improved physics for this device. We could do it with the physics we have. What we need is to get that physics reliably 75% of the time. That's the problem. And you learn that by building those things and running it. Just run it like that. And ITER would do that for us. ITER would be a good prototype for this thing that would get us started. But even if we did that, the first fusion device we built would probably get 20% availability. And the second one coming 20 years later would probably get 50%. Go into it like this. Again, this is also for fusion audience. You need to build some test facilities or to upgrade some test facilities that exist and run components so you can get this availability. That's what's needed. Fusion is a physics science, and all the interest is in doing physics. But for this, everything that needs to be done is to develop components that don't fail. And you do this by running it. And so create some facilities on that. Certainly as I envision, the fusion transmutation device would use the same nuclear technology as any other device. So it's not necessary to go in and invent some new nuclear technology, some new fuel type or something like that. You just take whatever you've got. The problem, of course, is wrapping it around in that funny shape. But once you look at that picture a few times, it's not so bad as it looks when you first see it. Or it just happens to people like us that have seen too many. I've really put a lot of caveats in this sentence. I think that the credibility of running with a fusion transmutation reactor or an accelerated transmutation reactor is going to come down to, are there some safety advantages that will allow you to get a better design of the transmutation reactor? because clearly either a fusion or an accelerated device is going to be a lot more expensive. You've got a reactor plus something, whereas with a reactor, you just got a reactor. And so clearly, going with a subcritical reactor is going to be more expensive. So the only reason it makes any sense is that it gives you something. And it gives you something that makes the overall cost, when we start talking about repositories and everything else, cheaper. And so the CAT subcriticality lead to certain advantages or certain design features which will lead to better transmutation properties. And very specifically, will it allow you to put in fuel without U-238 in it? Because putting in that U-238, you're half defeating your purpose because you're building up more of the things you're trying to destroy. So will it really allow you to do that? I don't know. You know, that's a good question. Good PhD thesis. Okay, but if it does, then the promise of it is quite good. And what the promise of it is, as I've sort of said several times, is you eliminate by fission these things that do the long life in favor of more things that die out in a few hundred years, the fission products. And the net effect of this is you reduce the heat, decay heat, by a couple of orders of magnitude. You'll also reduce the mass, but it's not the mass that really counts. The mass of stuff that has to go to high-level waste. But it's the decay heat that counts. And so you can increase repository capacity, and you can maybe think about a repository every several hundred years rather than one every several tens of years. So that seems to me to be the real promise. And the view graph that was up there when I started was one that shows that if you don't have much fissionable stuff in all this high-level waste, you have to process more of it to get a critical mass. Okay, it's obvious. You can also calculate it. So that's it. Thank you for your attention.
Okay. Okay, we have time for questions and comments. Okay, I have a question. You mentioned the economics. Has anybody looked at that? It does seem that it would be expensive, but if you look at the big picture, you may be saving money. So has anybody looked at it?
Not to my knowledge. I haven't seen.
That'd be a good PhD.
Well, I'd hate to be that PhD student. that would be a big.
That's economics. That's
yeah, but it's a big job. I mean, because it's really.
It's accounting.
Well, yeah. I mean, there's a lot of socio-political stuff that goes on here.
Yeah.
I mean, if you don't have to build another Yucca Mountain, it's just going to make a lot of people a lot happier.
Yeah.
And if you say that, okay, chain funded, this stuff really lasts for 1,000 years. The Roman Empire lasted that long. But right now we have to say these repositories have to last for 1 million years. That's a hard sell.
I think the economics, it's really a driver here, because if we were to fold in the cost of all of these fusion reactors plus our reprocessing plants and drive that into the cost of nuclear power generated electricity, go ahead and straight pass it on to the rate of electricity or cents per kilowatt, then you'd have to look, does it make sense to continue on with with our fuel cycle as we use it now? It looks to me like this would be prohibitively expensive.
Well, certainly building a fusion or an accelerator-driven reactor is going to be more expensive than building a critical reactor. But maybe you could do this with a critical reactor, critical fast reactor. And maybe a fast reactor, after the third or fourth of them, is maybe not too much more expensive than a light water reactor. So I'm not sure about prohibitive. And then you have to, this is where the economics gets hazy, because then if we're going to develop fusion, then we're going to spend a lot of money doing fusion R&D, okay, out of a different pocket, but we're going to do that. Well, this does it. This uses it as we go. So maybe if we take that into account, we've got a little credit that goes in. And, you know, it's a morass to do the economics.
I think that would be the key, would be to tag it on to this being promotion of fusion research. And at the same time, we're going to put some fuel around the outside and run this train.
Yeah, but that won't sell the big money. That's required. It's got to make sense. I mean, I think the key to going with either a fusion or an accelerator-driven device is that it's got to lead to a design that is sufficiently better at doing this job that it makes sense to do. And I think that's got to be associated with the subcriticality and with getting that uranium out of it where you don't have to reprocess so often. So that there's at least a possibility that it will. And that's the thing that I think needs to be worked next, is to see that, find that out.
You're adding enormous complexity by incorporating this with a fusion device.
Right?
Just in loading the fuel and removing it, among other things. But we know we can make fast reactors safe. And back when we had valuable fuel instead of a waste product, having a breeding ratio above 1 was a big boom. And this works. We could build one tomorrow. We could start to build one tomorrow. So it just sounds like it's adding a lot of uncertainties and complexities, whereas we have a system that works.
Well, let's see. There are sort of 3 or 4 things that are getting blended together there. Fast reactors work. Yes. Fast reactors are designed to breed fuel, not to destroy it. So it's a different sort of thing. But we could build a fast reactor to destroy it, too. And the Argonne design of the angle fast reactor for this would do it. But the destruction rate is not all that it could be, because you're also producing it from the U-238 that's in there. And the U-238 is in there because you need a Doppler, because you're critical. If you could relax that, how much is it worth to you? I don't know. You know, I think that's the question you would have to look at. Is a subcritical reactor that would allow you, say, to remove the U-238, where you didn't have to reprocess so much to get the same net destruction, is that going to be an advantage? In other words, there's no question about it that to add a fusion device or an accelerator device to a reactor is going to complicate it and make it more expensive. That's a given. But then the question is, does it give it any sort of advantage associated with being subcritical that would make up for that? And you know, and that's the issue that needs to be worked. And I don't know. You know, I don't know.
Tom?
I have 2 questions, Bill. One, is there still an option around to make an accelerator neutron source and not have a reactor, just use the neutrons from the
Yeah.
You didn't compare with that one. How does that...
Oh, you mean...
Don't couple it with a fission reactor.
You mean just use those neutrons? Oh, that's killing. Not enough of them.
Okay.
Basically,
I thought
a nuclear reactor is a wonderful neutron multiplier.
Yeah, I know. But I thought there was an option. You know, people a few years ago were talking about making a neutron source in Oak Ridge with a nuclear reactor. I couldn't believe it when they decided to use an accelerator.
So they don't
But
need,
they're doing it.
they don't need many neutrons.
Yeah.
That's just a few.
But that option is dead. There's no longer an accelerator neutron source without the fission reactor.
Well, for materials. Yeah, the old IMF is still bouncing around.
S&S, it's still...
S&S, the accelerator.
Yeah, but no, there was something called a tritium, that's a breeding one, but there was a waste treatment accelerator that did...
No, that's what I described, the ATWR.
But I didn't
It's got a nuclear reactor. Yeah.
Fission reactor.
It's got a reactor.
Always did. Okay. Thank you for clarifying. Second question is that because of the, you have to convert some of this fusion power, this fission part of this has to be integrated with a blanket system for the fusion reactor, right?
Well, the fusion reactor is about 100 megawatts, and that power is nothing compared to the 2,900 megawatts of fission power.
90% of that then was coming from,
Yeah. It's a subcritical fission reactor. I mean, that's really the way to think about it. It's a subcritical fission reactor. It's not what we used to think about.
Thank you. One thing you said in your presentation, you clarified it later, but I wanted to bring it up. You said we could do this in 40 years. We've been hearing that 40-year comment from the fusion community for about 40 years. Yeah, and I realized that you actually...
But we mean it.
Yeah, you clarified it later on by saying we would be using existing fusion technology and not the net electrical production technology that's still a little bit of pie in the sky. Did I understand that correctly? Would you care to comment?
That's right. The thing about, I have to come back and defend fusion.
Sure.
But
I would expect you to do that.
for people, I mean, it always has been 30 years away. But that's the wrong thing to measure in terms of. It's dollars. And those dollars have never been spent. And so as long as you don't spend the dollars, you never get there. This device, and so that was my purpose in doing this, is to see what you could do with what you got. And so we took the absolutely existing technology, the same technology and physics that the ITER device. ITER is an International Fusion Reactor that's about to be built. It's been designed for the last 10 years. It's been reviewed by 20 different communities of people. There's high level of confidence it will work. This one needs to do the same thing that ITER does. Same physics.
Yeah.
So I think that physics is there. The technology has been a $100 million program to develop technology in support of ITER. They've built all these big magnets and they've tested them and all that works. And so if they put all this together in ITER, that would be the job of ITER, is to integrate it together and then run it for a little bit. We'll get a lot of experience, and that's what we need. Now that won't be quite enough, because ITER will probably operate at 15% of it, something like that. And we'd like to get more. So you've got to build test facilities, run.
But you have assumed the steady state tokamak. How much of a stretch is that?
Well, that's the current draft question. That's the current draft question. Tokamaks are pulse devices, and that's a nasty thing because of thermal stresses and downtimes, cutting into availability and whatnot. But they're pulse devices because they work like transformers. They're the secondary of a transformer, and the field can't increase forever, and so you have to stop at a certain point. But there are other ways to drive current, non-inductive ways to drive current, and that's one of the big efforts in the physics program right now, is to develop those. And the development is coming along.
Has it come along pretty?
Yeah, that's come along. It's the question of how long. Can you drive it for an hour, or can you drive it for a day?
This is a steady state tokamak.
This is getting to a steady state.
You assume the steady state tokamak, like Tom just pointed out.
Well, I finessed that. I finessed that in the sense that I've got the availability. I did it as a function of availability.
Okay.
So if I had a tokamak that burned half the time it was running,
I got you. Okay.
and then only ran half the time of the year, and then that would be 25% of that.
Yeah. Okay.
So,
all right. Very good. I see several new faces in the audience, and those new faces you probably do not know that you're all before. So everyone is invited to join us for refreshments. But before we adjourn, let's express our appreciation again to Dr. Stacey. Thank you.
I listened to every word you said. I can understand you.